a new industry we're going into. This is the work of almost a decade as well. For a decade, we've been working with the medical imaging industry. The best way to extend life is to detect a disease soon. And medical imaging is the fundamental and the essential tools of doctors. There's all kinds of medical imaging approaches. There's PET, there's MRI, there's CT. MRI is good for soft tissue. CT is good for bone structure. You have ultrasound, of course. All of those methods, working with the leading medical imaging companies, from GE to Philips to Siemens to Canon in Japan, we have been working with them over the last 10 years to put computational methods and CUDA GPUs inside their instruments. The latest generation Philips ultrasound, incredible technology, has CUDA inside. GE's Revolution, this incredible MRI machine, CT machine, has GPUs inside. And so we're computationally accelerating medical imaging. However, in the last several years, advances have moved so fast, and there are millions of medical imaging equipment around the world that unfortunately will take decades to upgrade. And so what we decided to do is create a virtual remote supercomputer. It sits in a data center, or it could eventually sit in the cloud. This data center will run the entire software stack of a medical imaging system. From from reconstruction to applying AI for detection to visualization, we virtualized the entire software stack, and we created what we call Clara, and this will just run in the data center. And so you have the GPU server, the containerized and virtualized software, all of the APIs and acceleration layers, and the software that goes on top of it. Let me show it to you. On this side, what I'm showing to you is this. The input for both of these sides, this is traditional MRI machine running a filtered
backpropagation.
Or projection, sorry. Okay, and so is it projection? Filtered back projection?
Yes.
Okay, so this is a traditional technique for filtered back projection. It assumes that your body does not attenuate X-ray. But that's not true. The way that they solve this problem is simply to increase the dosage of X-ray so that your body does not attenuate the signal, and so that they could collect the back projection and reconstruct the image from it. This is a technology called iterative reconstruction. This doesn't assume a particular model that computes an X-ray model called radon model. This doesn't assume that. This iterative reconstruction method, one beam at a time, calculates, estimates, and corrects, and over time creates this. It's essentially the ray tracing, if you will, of medical imaging. And it computationally is several hundred times more than the traditional method. This is what's inside today's CT machines, except for the latest generation ones. The vast majority of the world's CT machines like this. If we could use this technique, iterative reconstruction, we could reduce the dosage of X-ray tremendously while increasing the resolution and fidelity of the reconstruction. And so what we're seeing here is simply this. What goes in is a sonogram, which comes out of a CT machine. The raw data of the CT machine comes out. It goes into this Clara server. It runs a piece of software called Astra. Astra is running filtered back projection. FBP, and this one's running iterative reconstruction, IRT, okay? And so let's go ahead, Mike, fire it away.
All right. So we're just gonna go ahead and launch this since it's already been set up. But what you're gonna see here on the left versus the right is the CPU versus the GPU reconstruction. And this is all happening within the browser. And as the layer is calculated, you can see them start to come back in.
So what's happening here, as you know, this side is doing 400 times more computation than this side. And it's doing it faster. This side, running on GPUs, is running several hundred times more computation than that. And look at the results. With the same amount of input from a sonogram, you could create much higher fidelity images. The other way to think about that is this. If this is the level of fidelity that you're comfortable with, you could reduce the amount of energy dose by a factor of 6. Another way of saying it is this. We can now use CTs for even children. Today, you can't use CT for children because the X-ray dose is too high. So the opportunity to be able to use medical instruments with computational advances is really quite groundbreaking. That's why GE calls this particular machine with IRT revolution. Okay, so now that we can do that, but we could do so much more. This is what the old machine looks like. Now that we can put this on Clara, we can apply AI to it. And so what Mike is doing here, he's applied this neural network that has been trained to detect organs volumetrically. We trained this neural network called VNet to detect 3D volumetric organs. I don't know any of the organs, okay? And so now we can use AI to train the organs, but it still looks kind of difficult to understand. So we could now apply ray tracing to render this image. All right, you guys, look at this. Are you guys ready for this? Before, after. Before, after. Okay? With Nvidia acceleration. Okay? Wow, 好漂亮啊. Okay, good job, Mike. Thank you. So, $7 trillion healthcare industry. We've now created a computer for healthcare. You could use it for imaging. You could use it for genomics. You could use it for AI. And it sits in your data centers, virtualized. We've turned healthcare, revolutionized it with modern computing. Once again, a fully accelerated stack, special libraries, working with the application developers in each one of the industries, and having a technical team developing it with partners.